Hi, I'm Luis Serrano, and this video is about the naive Bayes classifier. Naive Bayes is one of the most important theorems in probability and is very useful in machine learning. You may have seen it as a complicated formula regarding some ratios of probabilities. I like to see this a little further, and I like to think of it as what is the probability of something happen given that we know some information that something else happens. And then naive Bayes is an extension of this, which basically says, okay, once I have too many events and I don't know how to handle them, are there any naive assumptions that I can make on them to make the math work easier? And so this is what we're going to see today. So let's start with an example. Let's say we want to build a spam detector because we are tired of seeing a lot of spam email in our inbox and we want to sort it properly. So how do we build it? We build it with previous data. And let's say our previous data is a set of 100 emails. And when we look at them carefully, there are 25 of them that are spam and 75 of them that are not spam. So what we're going to do is we're going to try to pick properties of the emails that we think may correlate with them being spam or not spam. So let's pick one. Let's say we're going to study the appearance of the word buy. So we think that emails that contain the word buy are more likely to be spam than not spam. So let's study that. Let's see how many emails that are spam have the word buy, and turns out there's 20 of them. And let's see how many emails that are not spam have the word buy on them. So there's 5. So let's forget about all the others and just look at the spam emails. And here's a quiz. The quiz says, if an email contains the word buy, then what is the probability that this email is spam given the data that we have? And the options are 40%, 60%, 80%, and 100%. So feel free to pause the video and think about it yourself. Given the data that we have, what is the probability that if an email contains the word buy, then it is spam? This is a conditional probability. So I'll tell you the answer. The answer is, if we look at the emails that contain the word buy, well, there's 20 that are spam and 5 that are not spam. So that makes an 80-20 split. And so from this data, we can see that from the emails that contain the word buy, 80% of them are spam. So the probability, we conclude, again, just from this data, that the probability is going to be 80% that it's spam if it contains the word buy. Therefore, we associate the condition containing the word buy with the probability 80%. And that is exactly what Bayes' theorem is. You may have seen it in a different way, you may have seen it like a formula. This is really what it is. So just for fun, let's do it for a different property, for a different word. Let's say that we think that the word cheap may also be a good way to tell if an email is spam. So let's study this word. We count how many times the word cheap appears in spam emails. That's going to be in 15 of them. And from the non-spam, 10 of them have the word cheap. So we forget about the rest. And quiz, again, if an email contains the word cheap, what's the probability of spam? 40, 60, 80, 100. Again, feel free to pause the video. I'll tell you the answer. The answer is 60% because if you look at the split, there is 15 spam and 10 no spam among the ones that contain the word cheap. So that's a 60-40 split, and therefore the solution is 60%. So we applied Bayes' theorem for 2 words and obtained 80 and 60. Now here's where things get complicated. What if we want to apply it for both words at the same time? So we want to see what's the probability of an email being spam if it contains both the word buy and the word cheap? Well, we can do the same thing, right? We can count how many emails contain the word buy and then look at how many contain the word cheap and then actually look that they overlap. And so there's actually 12 emails that contain the words buy and cheap. So that's some good data. And then let's look among the no spams. Let's say that there's these 5 that contain the word buy and these 10 contain the word cheap. So actually there's none that contain both words, but that's okay. We're going to do the same thing as before. We have 12 spam emails and 0 no spam emails that contain the word cheap. So easiest quiz in the world. If an email contains the word buy and cheap, what is the probability of spam? 40, 60, 80, or 100. And this should be easy, right? Because there are 12 emails that contain both words, 0 emails that contain no words, and this is a 100% 0% split. So the answer is 100%, and we are done, right? Well, maybe you're being skeptical like me, right? It seems like that's a little too much. Like any classifier that tells you something's 100% is too strong. And where lies the problem? Well, the problem lies here. that we had 12 emails that contained the words buy and cheap, and that's not bad. But here we had 0 emails. So among the non-spam emails, there are 0 emails that contains the words buy and cheap. And so that's just unfortunate. Among our data, we don't find the 2 words, but it's plausible that these 2 words could appear, right? So we can restrict ourselves to not have a classifier with the words buy and cheap just because in our small data set the words don't appear. So what could we do? Well, one solution could be just maybe collect more data, like go through a lot more emails until we find the words buy and cheap and then do a Bayes theorem on those. But what if we just can't? What if we can't collect more data and we have to do with the data that we have? So let's think. We have this situation. What would you do if you have this situation? And you have to sort of imagine how many emails would contain the words buy and cheap. So what we're going to do is try to guess the number. Try to come up with a sensible amount of emails that would contain the words buy and cheap, even if we found none. So let's look at a slightly larger data set. Let's say we have 100 emails. So this is a different set than the first one. We have 100 emails, and let's say that 5 contain the word buy. And let's say that 10 contain the word cheap. And they don't overlap. However, what do you think would be a sensible number of emails that would contain the words buy and cheap? So let's think. 5 out of 100 is 5%, so 5% of the emails contain the word buy. And 10 out of 100 is 10%, so 10% of the emails contain the word cheap. So in an ideal world where everything was pretty, how many emails would contain the words buy and cheap? Well, what is 10% of 5%? It's 0.5%. So why don't we just assume that 0.5% of the email contain the word buy and cheap? So we can sort of imagine that there is half an email that contains the words buy and cheap. And since all we're doing is math, it doesn't really matter that there's half an email. This will work out in our formulas. What we did is an assumption. We assumed that the words buy and cheap are independent. They may not be, right? It could be that containing the word buy makes it easier to contain the word cheap because you're talking about a product. You say buy cheap something. Or it could be the opposite, that if one appears, that sort of forces the other one to not appear or to be less likely to appear. So it's quite a strong assumption. As a matter of fact, many people would say that that's a naive assumption. Assuming that 2 variables are independent when they may not be is very naive. However, that's what our algorithm is based, because it turns out that if we make these assumptions, things still work well, and it makes our math much easier, because now we don't have to collect thousands of emails. We can collect these 100, and from the number of pearsons of buy and the number of pearsons of cheap, we can sort of cook up the numbers of pearsons of buy and cheap. So let's do that. Let's go back to our data. We had 25 spam emails, and 20 of them had the word buy, and that's 4/5. And 15 of them had the word cheap, that's 3/5. So we can imagine that the product of this is 12 divided by 25. So we could assume that on average 12 emails here out of 25 would contain the words buy and cheap. So in order to find the actual number, we multiply by 25 and we get that 12 emails have the words buy and cheap. So that was kind of lucky that we actually did find 12. We're not going to be that lucky in the other case, but we can still do it, right? So we have 75 emails, 5 of them are buy, that's 1/15 of them. Then 10 of them have the word cheap, that's 2/15 of them. And the product of these two fractions, again assuming they're independent, is 2 divided by 225. So that's the fraction of emails that contain the words buy and cheap. So to find the actual number, we multiply it by 75 and we get 2/3. So in here we have 2/3 of an email contains the words buy and cheap. And that's fair. Let's work with that. So we go back to our data, and on the left we have 12 emails that contain the word buy and cheap. And on the right, we have 2/3 of an email that contain the word buy and cheap. And we can do math with these ones, right? Because now the quiz says if an email contains the words buy and cheap, what is the probability that is spam? So let's do some math. What is the split among 12 and 2/3? Well, let's take the spam ones. That's 12. And let's take the total number of emails that contain buy and cheap. And that's 12 plus 2/3, because there's 12 spam and 2/3 that are no spam. So we can find the ratio between these. And by the way, if you've seen the formula for Bayes' theorem, and there's a ratio and it's precisely this one. So what do we do with this fraction? Well, we put in lowest terms, it's 36 over 38, or 94.737%, because this split is 94.737 and 5.263. Therefore, our final answer is that the words buy and cheap give us a probability of 94.737% of being spam. That means if we have an email with both of those words, it's 94.737 likely to be spam. And that is precisely the naive Bayes classifier. So naive Bayes classifier basically is a combination of Bayes' theorem and the naive assumption that two events are going to be independent when they may not be. But that naive assumption makes the math much, much easier. So let's do a little summary. What we're really doing is we're going to fill out this table. And some places of the table we can't really fill out with data, so we fill them out with other places in the table. So let's look at spam and no spam emails. We looked at the total was 25 spam emails and 75 non-spam emails in our data set, right? Now the next row, we're going to count how many of them have the word buy. So 20 of the 25 have the word buy. That's 4/5. And 5 of the 75 that are no spam have the word buy. So that's 1/15 because it's 5 divided by 75. Now we're going to fill in the next row. So out of the spam emails, 15 of them contain the word cheap. That's 3/5 because it's 15 by 25. And 10 of the 75 that are not spam contain the word cheap. And so that's 2/15 because it's 10 divided by 75. Now we would love to fill in the last row with data, the words buy and cheap. But unfortunately, our data set is not big enough to actually handle as an event that is so sparse, like the words buy and cheap appearing. And you can imagine if there were more words, it would be even harder. So we have to cook up this row from the previous ones. So what we're going to do is the naive assumption that the words buy and cheap are independent, so that one doesn't imply or push the other one to appear or stop it from appearing. And if we make this assumption, then we're going to say that the product of these two is the probability of the word buy and cheap appearing. So that's 12 divided by 25 is the product of 4/5 and 3/5. So that's going to be our probability. And now, if this is the probability of buy and cheap appearing, how many emails contain buy and cheap? Well, we have to multiply by the total number, which is 25. So 25 times 12 divided by 25 is 12. So we conclude that 12 emails should contain the words buy and cheap. Even if there is 12 or 14 or 10 or none, logically, if we have that assumption, there should be 12. Now, let's look at the other two boxes. Well, again, we make the assumption that the words buy and cheap are independent of each other. So the product of these two, which is 2 divided by 225, is going to be the probability of the words buy and cheap appearing in an email that is no spam. So now, how many emails that are not spam contain the word buy and cheap? Well, it's the product of the probability times the total number. So how much is 2 over 225 times 75? That's actually 2/3. So we have 12 spam emails and 2/3 of an email that is not spam that contain the words buy and cheap. So now we have to normalize, right? We have to see what is the split, how many percentage are spam among the total ones. And the total ones is 12 plus 2/3. That's all of our emails that are containing the word buy and cheap. So we divide 12, the spam ones, divided by the total, which is 12 plus 2/3, and we get 36 over 38, which is 94.737. Now notice that naive Bayes extends, and the idea is that this extends to many, many more properties, right? Because the point is if we have 50 properties and we can't check when they all appear at the same time, we can check when one appears and then multiply things, right? So let's add an extra row to this table. Let's say we looked at the word work and we're wondering if the word work helps us in our classifier. So let's study how much it appears. Let's say that it appears 5 times in our spam emails and 30 times in our non-spam emails. So it doesn't look like it's going to help us that much. It looks almost like it's a word that's more correlated to non-spam, but let's study it. So this 5 out of 25 is 1/5. So therefore, 1/5 of the spam emails contain the word work and 6/15 of the non-spam emails contain the word work, because 30 divided by 75 is 6 over 15. So again, naive assumption that the words buy, cheap, and work are all independent. Therefore, the probability that the 3 of them appear in an email is the product of these 3 numbers, which is 12 divided by 125. And again, if we want to estimate the number of emails that are spam that contain those three words, we multiply the probability times the total, and we get 12 divided by 5. So roughly 12 divided by 5, which is a little over 2, emails will be spam and contain the words buy, cheap, and work. And now let's do it over here. We assume again that the three words are independent of each other. We take the product of the probabilities, and that's going to be the probability that the words buy, cheap, and work all appear in an email at the same time when the email is not spam. So in order to find the total number of emails that are not spam that contain the words buy, cheap, and work, we multiply the probability that they appear times the total number of emails, and we get that 4 out of 15 emails are not spam and contain the word buy, cheap, and work, because 75 times 12 divided by 3375 is 415. So in summary, out of the emails that contain the words buy, cheap, and work, 12 over 5 are spam and 4 over 15 are ham. So how many are spam divided by the total? Well, we take 12 divided by 5, the number of spam, divided by the total, which is 12 divided by 5 plus 4 divided by 15, and that is going to be 36 over 40 if we put in lowest terms, or 90%. So that's how we combined the three words. Notice that 90 is less than 97 because the word work actually decreased the probability that an email is spam, because as you can see, work appears a lot more in spam emails. So it does make sense because it's not a word that one would correlate with spam. So some of these properties may increase the probability and some of them would decrease it. But the fact is that naive Bayes helps us combine a bunch of different features into creating a model that calculates the probability that something is spam. And these features get combined in a nice way because we don't have to wait until we find an email with all these features. We can actually cook up probabilities without having emails that satisfy all of them. So if you like formulas, this is really what happened in the background. This is the formula of Bayes' theorem, and the letter S stands for being spam, the letter H stands for ham, which is actually how they call emails that are not spam, they call them ham, and the red letter B stands for buy. So probability of S given B, when you see that vertical bar, that is a conditional probability. So what the left says is probability of spam if the word buy appears, and that's a ratio because most probabilities are ratios. And in the top we have probability of buy given that it's spam. So out of the spam emails, how many of them contain the word buy? That was 20 out of 25. And then probability of S is the probability of that an email is spam regardless of any words that it contains. So that's 25 or 100, because if you remember, there were 25 spam emails out of 100 total. So in the bottom goes everything, the total. So that's the same thing, 20 over 25 times 25 or 100, plus the ham ones. So we have, what's the probability of the word buy appearing if the email is ham? That's 5 out of 75, because out of 75 ham emails, 5 of them had the word buy. And the probability of an email being ham, well, is 75 over 100. So if you do that whole formula, you get 80%. But the interesting thing is, if you look at what we did, it was exactly that. And then what happens with naive Bayes is that we make this assumption that the probability of the word buy and the word cheap appearing is the product of the probabilities of the word buy appearing and the word cheap appearing. Again, this is not supposed to happen. The words buy and cheap may be either correlated or inversely correlated. Maybe one implies the other one, maybe one stops the other from appearing, but we're going to assume naively that the product of the probability is the probability of both appearing, which is saying this, that the probability of some event B intersection some event C is the product of probabilities of B and C appearing. Again, this is a naive assumption, but we're going to make it because it makes our math easier. And the full formula for naive Bayes, this is for 2 events, but you can generalize this for many more events, is probability of spam given that the words buy and cheap appear is that formula. And if we look at all the probabilities here, we say probability of spam if it contains the words buy and cheap. Well, it's a ratio. On the top, we know this probabilities is 20 out of 25 for probability of buy given that is spam. Probability of cheap given that it's spam is 15 over 25. If you remember correctly, there were 15 spam emails containing the word cheap. And then again, 25 over 100 for the probability that an email is spam. In the bottom, we have the same thing, plus 5 over 75, the probability that a ham email contains the word buy. 10 over 75, the probability that a ham email contains the word cheap, and then the probability that a ham email is ham, which is 75 over 100. You do this math and you get 94.737. But I challenge you, if it doesn't look super clear, look at this slide and go back to what we did in naive Bayes and convince yourself this is exactly what we did. What we did in this whole video was nothing different than calculating probabilities by dividing one thing by another. So thank you very much. That's it for naive Bayes. As usual, if you like it, please subscribe for more videos coming up. Please hit like, share it with your friends, and feel free to comment, ask any questions or any suggestions for this or any other videos you'd like to see. And my Twitter handle is Luis Likes Math. So thank you very much for your attention, and see you in the next video.